We're going to continue where we left off last week and try to finish chapter 11. So chapter 11's a really big chapter, so hopefully everyone's been taking time to go through the material. Um, did I want to mention anything else? I don't think so. The homework is the homework for chapter 11 should be pushed back to Thursday. So it'll be due Thursday at 11 p.m. Oh, also on Piazza, someone asked about how to do electron configurations because it seemed a little bit confusing and whether or not they should memorize anything. So I posted a little electron tutorial on Piazza. So if anyone's interested or struggling with that, they could take a look. But I try not to stress memorization. I try to stress, practice. If you practice, you'll just get the hang of it and you won't have the need to feel to memorize anything because it'll be kind of worked in your brain how to do the problem. But you just need to be able to draw right electron configurations. So you need to be able to interpret where the s orbitals start, where the p orbitals start, and where the d orbitals start, and how to read the energy levels as you move across from the periodic table, then zigzag down the periodic table. So I will probably ask you questions about atoms or elements in up to row 4, so n equals 4. I probably won't ask you about anything else other than that in regards to electron configurations. So if you can write all electron configurations of those elements, if I ask you on the exam, you're in good shape. But let's continue. So last week we left off on Lewis symbols. So if there are any questions about Lewis symbols, always contact me. I'll be happy to help. So Lewis symbols are good for writing the valence electrons. For example, if we wrote oxygen has 6 valence electrons. And we could tell because oxygen is part of group 6A. So it will have or 16. So oxygen is group 6A. So I have 16. So it'll have 6 valence electrons. So you could use the group number to tell how many valence electrons an element in a family has. So how we would depict this on our Lewis symbol is we would write 6 electrons around the oxygen atom. So remember, the valence electron consists of 4 orbitals, 3 p orbitals, and 1 s orbital. So we can only draw electrons around the oxygen in 4 places. So then next we pair up the electrons like so, and we have 6. So that's an example of oxygen. You could do those with nitrogen or any other element. We can do nitrogen has 5 valence electrons. Oh, sorry, I didn't put the E here. So E minus means electrons. So 1, 2, 3, 4, 5. Okay, so let's move on. All right, so now we're going to use these valence electrons and kind of relate them back to trends in the periodic table. So so let's talk about that. So we're going to talk about trends in atomic size. So atomic size has to deal with the size of the element and the distance between the nucleus and the highest valence electron, or the valence electrons. That distance will give us our atomic radius, and that will constitute the size of the atom. So some trends are the atomic size decreases from left to right. On the periodic table. So as you're looking at the periodic table, as you start from the left side, as you're increasing to the right, the size tends to decrease. And that's because as you add more electrons to the same energy level is going to be populated by more electrons, and that's going to increase the nuclear attraction because our atomic number also increases. So increasing number of atomic number means we have more protons in the nucleus, and that gives us an overall net or more effective nuclear charge that attracts the electrons and pulls them closer to the nucleus. So that is the explanation for why the size of the atom tends to decrease as you move across the periodic table, because you have a higher effective charge in the nucleus pulling on the more electrons in the energy level, and that causes the atom to kind of contract and shrink. Okay, we also talked about in off hours if people are not understanding that kind of explanation, or we could talk on Piazza too. So the opposite trend is atomic size increases from top to bottom. So this is a common question too to ask. Like of these elements, which element has the least, or which element has the rank these elements in increasing or decreasing atomic size or atomic radius? So that's a common multiple choice question too, or a ranking question that we tend to ask from top to bottom. So the size of the elements do play a role in like reactions and stuff, but we won't talk about that. But they do put a role in the stability of elements that form and reactions too. Okay, so now let's talk about the reasons for these trends. So here are the reasons. Okay, so the reason is highest occupied energy level. So when you occupy higher energy levels, let's just write this down. Valence electrons occupying higher principal energy levels, higher principal energy levels. So the further you are above, as you increase the energy level, n equals 1, n equals like up to 4, those levels are increasingly higher in energy and away, say this is the nucleus, away from the nucleus. So it's going to be further away, and that will overall increase the size of the radius. So your distance is increasing, therefore your size of the atom itself is going to increase. Are further away. Oh, sorry, not further away. Or farther. Oh, sorry, I meant farther away. Farther away. Or sorry, just say farther. Sorry, farther from the nucleus. So that distance is what causes the size to increase. And likewise, the other reason is, so I'm just going to highlight a reason here. So this is one of them. And the next one is nuclear charge. So nuclear charge plays a role too. It's kind of what I explained for the first trend, but we're going to summarize it here. So 1 as the number. So that's number of protons. Number of protons in an atom, so the increase in the atomic number increases, so the positive charge will increase. In the nucleus, so what this means is the valence electrons are pulled. So they're going to be pulled closer to the nucleus, like I said in my earlier explanation. And that will shrink the size of the atom. Nucleus and atom become smaller, right? Because they're pulling on those electrons, so the radius will decrease. The atom becomes smaller. Okay, so hopefully that explanation kind of makes sense. That's how we explain the trend in atomic size. Okay, so let's go back to let's look at a representation of these atomic sizes, and so we can show what we mean by their sizes. So we're going to share to the lecture slide. Okay, right here. So you see here in my periodic table that my smallest element is actually helium because it's to the right of the periodic table and above. And you see as we go down a column, it gets increasingly bigger because the principal energy level is going to be higher. So all the way down to cesium, which is the largest. And as we move across the periodic table, we see that they decrease because across the periodic table, we're adding electrons to the same energy level. And as we move across, our atomic number increases and the positive charge in the nucleus increases, which pulls on electrons much tighter and with much more force. So it has a stronger attraction that will cause the radius or the size to decrease. And as we see here, they decrease ever so slightly to the right. And as we go to the bottom rows, they also have that trend of decreasing right here. See? And it will go down the column, sorry, they tend to increase like so because we're adding a new principal energy level that's further away from the nucleus. Okay, so those are the trends of the atomic size. So just remember left to right, decrease, top to bottom, increase. Okay. So here's a general picture of the trend. So, when you get your periodic table on the exam, you're free to write these trends if you forget it, but or you could write them maybe on. So for the midterm, I am thinking of allowing a note card for students to use, so you can maybe be able to write that on a note card if you want. But just be aware that when people make note cards, they don't necessarily use them. So if you study well, you probably won't have to use one. And making the card itself takes time too. So that's something else to consider. Okay, so let's now go to an active exercise. So hopefully you guys are doing these. They are important. I wish I could do them with you live, but unfortunately, I don't trust my internet to do that. So we have to do it remotely instead. Or pre-recorded. Okay. So here's an active exercise for today, one of them. Okay, so I want you to refer to the atomic table. And list atomic numbers. So this is the common exam question. It's 15, 16, and 33. in order of increasing atomic size. Okay, so let's just go back to that chart so we can refer back to it. So we won't. So you'll be given the periodic table, so you can actually rank them according to the periodic table, but you won't actually be seeing the atomic sizes. So what we'll have to do. So let's just go back to that atomic table. So let's locate elements 15, 16, and 33. So 15 is, okay, 15 is sulfur, not phosphorus. Let's just make sure here. So let's go. So you can refer back to your periodic table or the size of these elements. But 15, I believe, is sulfur, but let's just make sure here. Okay. So you're always free to use the periodic table. So 15 is phosphorus. So 15 is phosphorus. 16 is sulfur. And then we have 33 is arsenic, I believe. Yes, 33 is arsenic. So then we have 33, which is arsenic. I always get astatine and arsenic mixed up, but 33 is arsenic. So if we look at our table here, we see that phosphorus is to the left and the third row. So compared to sulfur, sulfur is right next to it. So sulfur is going to be smaller than phosphorus. And we can see that based on our trend here, 110 and 103. So these are picometers, very small lengths or distances. And then we have arsenic, which is down below on the fourth energy level, and it has a radius of 120 picometers. So based on the trends, we can arrange them as 16 is greater than, 16 is less than 15, which is less than 33. So arsenic's the largest because it's below on the fourth level, while P and S are on the same level, level 3. So, okay. So that was the active exercise. Active exercise, you just have to look at the periodic table and remember the trends and be able to rank elements in increasing size or decreasing size of their atomic radius or atomic size of the elements. Okay, so you won't get this periodic table, so don't worry. You won't get this diagram, but be able to use the periodic table to figure out which element is larger or smaller. Okay. Okay. So hopefully that explanation was helpful. So just to summarize, sulfur atoms are smaller than phosphor atoms, as sulfur have a higher nuclear charge because it's to the right of phosphorus to attract the highest energy 3s and 3p electrons. So we could just write that just to clarify here. So let's just write in red. So here we go. So sulfur atoms, so sulfur atoms. So sulfur atoms Z equals 16 or smaller than phosphorus atoms. as sulfur atoms have a higher nuclear charge to attract the highest energy 3s and 3p electrons. So the valence electrons. Like so. And the highest occupied energy level in a phosphorus atom is N equals 3. And for arsenic, and for Z equals 33, which is arsenic atom, it is N equals 4. So that is why it is the largest. So that's why the order is 16, less than 15, less than 33. Okay, so hopefully that all made sense. So let's talk about our next topic, which is another trend, and that is called the first ionization energy. So let's talk about that. First ionization energy. So the first ionization energy is defined as the energy required to remove one electron from a neutral gaseous element. From a neutral gaseous atom, sorry, not element, gaseous atom of an element. So essentially what this means is that if we lose an electron, we form something called an ion, which is a positive charge. So in this case, it's a cation. We'll talk more about what ions and the different types. Was the energy required to remove an electron from a neutral atom of an element. So remember that the electrons and the number of protons are balanced in the neutral element on the periodic table. So if we remove an electron, we now have an excess of positive charge or protons. So now we have a net charge. And that is what happens when we lose an electron. That's called ionization. And the ability to lose ionization is tied in with the ionization energy, or the amount of energy required to eject an electron from a neutral element. So the trend is, so it increases. So it's pretty much the opposite of atomic size. So if you could think about like atomic size is inversely related to ionization energy, you'll be solid. So remember, if atomic size decrease from left to right across a period, it's going to increase with ionization energy. So it's just the opposite of the trend. Increases from left to right. From left to right in any row. In any row of the periodic table. And so as size tend to increase down the group, ionization energy is going to decrease. So atomic size increases. So now ionization energy is going to decrease, and we'll explain why. So decreases when moving down any group. So let's go into the reasons. So reason number one. So the reason has to deal with or talk about the highest occupied principal energy level again. So here's the subject: highest occupied principal energy level. So energy decreases down a group as the electron that's removed is further or farther away from the nucleus. That is removed is farther from nucleus. So remember that the further away we are from the nucleus, or farther away, the attraction between the positively charged nucleus and negatively charged electrons is going to decrease, because remember, Coulomb's law. Coulomb's law of attraction is Q1 Q2 over R squared. So that gives us our attractive force, right? So our attractive force. So as our R term here, as we increase the R term away from the nucleus, the attractive force of Coulomb's law is going to decrease by a square relationship, square term. So if you double the distance, you're going to have a decrease of the attractive force by power of 4. So it's always going to be felt less from the electrons as you move higher up into those principal energy levels. Okay. So hopefully that made sense. The next one is nuclear charge. So now we have nuclear charge. Again, the nuclear charge plays a role too. So nuclear charge. So within a period, outermost electrons are in the same principal energy level. So what does that mean is that the first ionization energy increases across the period. As the electron to be removed is attracted. So remember, as we move across the period, there's going to be an increasing quantity of positive charge because the atomic number is increasing. So as we move across the periodic table, the amount of energy to remove an electron, or the first ionization energy, is going to undoubtedly increase as we increase the atomic charge or the atomic number. As the electron is removed, to be removed is attracted attracted by an increasing by an increasing quantity of positive charge. Okay, hopefully that makes sense. So within a period, outermost electrons are in the same principal energy level. So as we move across, the electrons are going to be added to the same level and therefore increasing the positive charge in the nucleus by increasing, because we're having a higher atomic number, more protons. The attractive force of the electrons will be increased. So to overcome that attraction, more energy has to be supplied to eject and form an ion from the neutral gaseous atom. Okay. So let's look at an example. Let's look at a picture here. I think it's a very good depiction of what we're talking about. So let's go right here. So see here the formation of a sodium ion from a sodium atom. So here's a neutral sodium atom. So hopefully you know that you can write this electron configuration. Sodium's in the third row, the first element of the alkali metals. So 1s2, 2s2, 2p6, 3s1. So remember when we eject an electron, we're going to, the most accessible electron is the one in the highest outermost energy level, or the principal energy level in the s and p orbitals. So here, our principal energy level, our highest principal energy level is the 3 level, n equals 3, and we have an electron in the s orbital, 1 electron. So as we supply enough energy, we're going to eject that electron right here. So we have lost an electron. So now we have a imbalance of, okay, so there's a typo, right? Well, there's not a typo. So there's 11 plus 10, 10 plus 1, 11 negative charges. So as we eject it, now there's a imbalance of positive negative charge. So we have a net positive sodium ion and an electron that has been ejected. And we see here that we write the electron configuration of the ion having lost that electron in the 3s1 energy level. So there's no electrons occupying it. So we simply write the electron configuration as the filled 1 and 2 energy levels. So also fair game on the exam is electron configurations for ions. So we'll talk more about ions, but try to be comfortable writing species that has lost electrons, gained electrons, or just neutral and have a complete balance of protons and electrons for the element. Okay, let's move on. Okay, so here is a plot of the ionization energies in kilojoules per mole. So that's a term for energy and our atomic number. So see here, as we go from period 1, H to helium, the atomic size will increase because we're increasing atomic number. And as we go down to the second period, see that big decrease because the valence electrons are now in the second energy level. And it increases as we go across the row. See beryllium, boron, like so. So you'll see some discrepancies, but I will not worry about the discrepancies. It has to deal with electron-electron repulsion in the orbital. So electron-electron repulsion will cause some disturbance between two electrons, and that will actually disturb the attractive forces between the two to the nucleus. So that will cause a slight decrease in ionization energy, but I don't expect you guys to know that, so you don't have to worry about those exceptions. So here we go to the end. Neon's the highest in at the last of period 2. Now we go down to period 3. We see now that same kind of trend going across the period. Now it's down 4, even lower than sodium. And as see here, we go across to the transition metal elements, like so, and go all across over to the 4p block, all the way up to krypton. And you see that the trend, as we move down the period, or move down several periods, the trend is the noble gases, they will tend to decrease here, like so. Okay, so you don't have to memorize this chart. Just memorize the trend between increasing ionization energy and relative to the atoms on periodic table. Okay. So let's go back now to the iPad. So let's talk about now. We're going to be talking about the second and third ionization energy. So what is that? So second and third ionization energy. Ionization of energy. So hopefully when you watch these lectures, you try to follow along. You know, the lectures are long. So like to speed it up, guys should probably play at 2x speed so it kind of goes faster. Or you don't have to watch it all at once, you know. If you feel comfortable with this topic, you could probably skip over a few minutes if you think you got the gist of it. But you know, you guys should watch. I hope you guys watch it because it'll help you understand the stuff better by me explaining some things. But you know, if you have another way of learning material by reading a book or something, by all means. I'm just a facilitator of the knowledge, so hopefully, if there's another way of you guys learning the material, that's great. I encourage it. Encourage you guys to be independent as well. So, but hopefully, at least most of you, if you don't read the book, hopefully these PowerPoint, you read over PowerPoints and maybe go through this video. You kind of see the stuff I touch upon and some things I emphasize and some things I don't. Okay, that'll help you prepare for the exams and the quizzes. All right, so anyway, let's talk about the second ionization energy. Ionization of energy. I don't know why they say energy. That sounds kind of weird, but so it's the energy required to remove an electron from an ion. So removing an electron from a neutral element is relatively more easy than removing it from an ion with a 1+ charge. So as you move towards the second, third ionization energies, they tend to increase dramatically because it's much harder to remove something with a net positive charge because the attractive force is even stronger than before. Electron from an ion with a +1 charge. Likewise, the third ionization energy is much of the same thing, except this time you're moving from an atom with a 2+ charge. So energy. So ions play important roles everywhere, especially in the body. You know, a concentration of ions, you know, the sodium potassium pump, that concentration of ions between membranes, you need a specific balance. There's also calcium ions. So ions everywhere in your body that plays a role in homeostasis, body regulation, and you know, bodily system regulation as well. So these ions, they do play an important role in biological systems, ecological systems. So these charged particles actually do in fact play a very delicate role in balancing health. You know, it's like an imbalance indication of like disorders or diseases or disabled bodily functions. So much research is involved in the study of ions, like ion channels. So that's a very important area of science in general. So third ionization energy required to remove an electron from an ion with a 2+ charge. All right, so it's even harder to remove an ion from this, or electron from this kind of ion, because it has a 2+ charge. Okay, so let's quickly look at this diagram to give you the trend in ionization energy. So it's the opposite of atomic size, left to right across the periodic table. We increase in ionization energy, and then as we go from top to bottom, we tend to decrease in ionization energy. So as we go from the bottom of the periodic table to the top, there's an increase in ionization energy. Okay, so now let's talk about an active exercise dealing with this trend. Okay, so let's see here. So here is, let's talk about active exercise now. Oh, whoops, that's not what I want to do. So active exercise number 2 of the day. So I want you to list each of the following groups. Groups of elements. In order of increasing first ionization energy. So we have beryllium. So know what these symbols mean. N, nitrogen, and F, fluorine. So these elements are all in the same group, same row. So they are in period 2. So hopefully you guys can work this out on your own first before listening to this. So go to the periodic table and we're going to list their atomic numbers. So we know beryllium is across the periodic table in the second row. So beryllium has an element of, so beryllium is Z equals 4. Nitrogen is Z equals 7, right? So use your periodic table. And fluorine is Z equals 9. So as we see they're in the same row, right? So as we go across the periodic table, our trend is that the ionization energy tends to increase. So our order will be beryllium, since it's the furthest to the left, is less than, well, not less, yeah, less than nitrogen, which is less than fluorine. So fluorine is the most ionization energy, and beryllium is the least. So let's talk about the reason. So ionization increases across a period due to the increasing nuclear charge holding electrons that are in the same principal energy level. Okay, so hopefully that makes sense. So let's move on here. All right, so now we're going to talk about the family. So what that means is like why are these elements arranged in these groups along the periodic table? Why are they arranged so? So we're going to classify them now. So maybe some of them will be familiar. So chemical families. And so the chemical families are also distinct because they have they all have, every element have the same number of valence electrons. So chemical families, they are groups of elements. Not groups, let's just say group. Group of elements. Group of elements having similar chemical properties. Due to similar valence electron configuration. So the fact that they have similar valence electrons configuration, that gives us a kind of like an insight how to predict their chemical properties. Similar valence electron configuration. So the reason is because they appear in the same column of the periodic table. So first, we're going to talk about alkali metals. So alkalized metals, they belong. So they're the very first column on the right, so left of the periodic table, belong to group 1A/1 of the periodic table. Okay, so here are some of their properties. So there's an exception. Exception is hydrogen. That is not an alkali metal, but it belongs in that column because of its electron configuration. So the lone exception is hydrogen, the oddball. Valence electron. So valence electron, so it only has one valence electron. So we denote it as NS1 because any element that has any element in that column will have this electron configuration N, which is any integer with at least number 1 up to maybe 7, NS1, like so. So a unique thing about alkali metals, so when alkali, so the common ones are sodium, potassium, rubidium, cesium, lithium, stuff like that. So valence, so when alkali metal atom loses its valence electron, valence electron, the ion. So the ion formed is isoelectronic with a noble gas atom. Isoelectronic means has the same number of electrons and electron configuration of a noble gas or with something else. So in this case, noble gas atom. So isoelectronic means having the same electron configuration as another species or another element of an atom. Okay. So when we lose this valence electron, you notice we'll gain electron configuration that is identical to the noble gas in the previous row. Okay, so let's look at this depiction of the chemical families here. So here is our chemical families. See here, this is the alkali. All the elements in this dark yellow here, 1, 2, and this yellow part of the staircase, those are main group elements. Transition metals is this D block here that we covered last lecture. Metalloids are these blue elements. Remember, they have properties of both metals and non-metals. And then metals is all the green elements right here. All right, so 1A is the alkali metals, lithium, sodium, and potassium. You see here that when they react with water, they react quite violently, releasing hydrogen gas. Don't worry about this reaction. You don't need to memorize it. But see, as we go down from down this column, the reaction is much more intense. So as you go down the periodic table, this reaction with water gets visibly more reactive. And if you go down to like the more other reactive metals that are not commonly encountered, like rubidium, cesium, they get even more reactive. But you see here that the general trend is that they react the same with water, given the hydroxides. So hydroxides are strong bases. You might have encountered sodium hydroxide, potassium hydroxide in like degreasers for ovens and stuff. And so that they do react in a predictable manner. There's also, this one is called the halogens. So we call this, they have halogens because they have similar properties when they react with, say, with other metals or other non-metals. So for example, when they react with phosphorus, they produce this burning reaction, which is a flammable phosphorus trichloride. You see here, phosphorus tribromide, they evaporate, and it's very volatile mixture here. And then zinc iodide too, you see that it gives off a lot of heat. So the reactions are very predictable, and they all undergo similar ones with metals or non-metals. In this case, it's a non-metal with phosphorus, but in this case, it's with zinc. You form zinc iodide, and you get this solid right here. That's kind of getting dispersed in the air. Right here, phosphorus tribromide. The amount of heat the reaction causes it to kind of, kind of combust here. And here is a very violent one where they react and you form this compound that's a liquid and it's giving off a intense amount of heat. But don't worry about the observations. These observations, they tell you that the chemical reaction is taking place because you generate heat, evolution of a gas, and this is most likely probably a gas too, right here. This nice, very purplish mist thing. Okay, so those are my takes on the chemical family. So let's go back and talk about them a little bit more. So see here is alkali metals, alkaline earth. So these are elements that are found in like rocks on our earth, and they combine to form basic hydroxides. So for example, calcium hydroxide, barium hydroxide. So they form calcium hydroxide, as I already said that, barium hydroxide. So they form minerals that can be found as hydroxides on the earth, in rocks and like other sediments that we see today. So those are alkaline earth metals. Whoops. In this block is transition metals. Don't worry too much about that right now. This is the lanthanide and actinide series. Those are they belong to a class of elements that are kind of rarely encountered on Earth. So they get their own groups here. Don't worry too much about those. Remember, these are a mixture of metalloids and non-metals. They don't really have a group name besides their name as boron, carbon, nitrogen, and oxygen families. Right here is the halogens. So halogens, they have similar reactivity, and noble gases. Remember, noble gases, they have a filled octet, so they're very happy elements, and they usually do not combine with anything, usually. So you usually see helium gas, neon, and argon. They really don't form compounds. They really are just single elements. atom elements or single. They're basically in nature they don't combine with anything. They're seen purely as their element. Argon, neon, uh, and then neon, argon, and helium. Right. Some elements can form compounds. We'll see that xenon actually can form compounds with like oxygen and chlorine and halogens and other stuff. But that's one of the rare ones. And who knows? Maybe in the future we'll see other noble gases that form some cool compounds. So the future, there's stuff yet to be discovered. Okay, so now let's go back to the whiteboard. Let's talk about chemical families. Okay. So alkaline earth metals. So I don't expect you guys to know why they're called alkaline earth metals. That's just the name we give to them, and it's based on a similar property. They form very alkaline solutions. So like, so very basic solutions. The fact is, they're alkaline. So I did research this before. So what we want to say is, let's see. So let's go to alkaline earth metals. So alkaline earth metals, they yeah, okay. So if we go to like Wikipedia, we can see that the alkaline earth metals are named after their oxides or their the alkaline earth. So basically they're the oxides. So like I said about the hydroxides, oxides that are formed yeah, so they form like these basic oxides when they react with water. Uh and we called it earth because these oxides, these alkaline earth, they're really not they're technically not soluble in water. So we call them earth because they kind of don't dissolve in water, just like like the sediment on earth. You can't dissolve that, so we call it like earth to describe that property. So that's the kind of the history behind um, between the alkaline earth metals, if anyone is interested. So let's talk about that. So alkaline earth, let's just capitalize that, or not. But don't worry, you don't have to worry about the etymology or history behind it. Just know that this group is called alkaline earth metals. Belong to group 2A/2 of the periodic table. So some trends of these or some properties are valence electrons. We have the NS2. So now we have the filled S shell. Then we have 2 valence electrons. Are given up to form ions. Form ions with 2 plus charge. So we have 2 valence electrons that can be given up to form ions. So they generally form ions with 2 plus charge. And that's because losing that, they'll have electron configuration of a noble gas. And when atoms or elements lose electrons or gain electrons, they want to be like the noble gases because they're like held to this high standard where they're very happy or stable. And having a full occupied shell of electrons makes the atom particularly stable. So next we're going to talk about halogens. So let's talk about the halogens. So the halogens are what we call salt formers. Because like sodium chloride is a salt and it's composed of a halogen, chlorine. So they are elements in group 7A or 17. So I have 17 of the periodic table. And now they have valence electron of valence electrons are SNS and S2 because they have a filled S shell, and then they're all the way to the right in the P block and P5. And when we gain an electron, has a configuration of a noble gas. And forms an ion with a 1- charge. So when we gain an electron, a halogen gains an electron, it forms an ion that has a noble gas configuration. Okay, so hopefully that was okay. Halogens, salt formers, alkaline earth metals. Okay, so here let's go back to what typical of these elements look like. So what do these elements look like? All right, so here is the alkali metals. Here are the alkaline earths. So beryllium is the oddball out of it. They don't really mimic the same reactivity as magnesium or calcium, strontium, barium. Radium, I won't worry too much about radium. Radium is another oddball. You rarely encounter it. But there is some chemistry known, but we won't focus too much on that. So here, see sodium and lithium. They're both metallic. They're both pretty malleable. They can be easily cut like that. Here's magnesium and calcium. They look kind of like sort of like little microchips. And you see that they're very different in appearance. Magnesium is kind of luster, has this luster to it, whereas calcium does not. So these are examples of those two the two groups of metals that are common, that we see every day: magnesium, calcium, potassium, sodium, lithium, barium, stuff like that. Okay. So lastly, we're going to talk about the noble gases. So let's go back here. So noble gases, they are kind of like, let's get a way to put it. They're kind of like the standard of elements. Like they're kind of like what all elements strive to be as stable compounds, because noble gases, they exist mainly as just pure elements. And not as compounds, as I talked about before. So here's a noble gas. Noble gas. So they are called noble because they don't react. So unreactive elemental gases, so they're only composed of their elements and not of any other elements. Gases appearing in 8A. So another type of question I like to ask is I'll tell you like name the noble gas in group 8A period 5 or period 4, yada yada. That's one common question. So you have to be able to read one period, how to read periods, like their rows across the periodic table, and how to find the group numbers 1A, 2A, 18, 16, etc. So it's important that you know how to identify these families and the group number they're in. 18 of the periodic table. Okay, so their valence electrons are a filled shell, so they're very, very stable. They do not want to react with other elements. So they have a full shell, NS2, NP6. So they have 8 valence electrons. So they already have an octet. So they're very happy. Lastly, let's talk about hydrogen. Hydrogen is its own group because it's neither an alkali or or halogen, but it shares properties of both. So it can gain an electron, but it'll have no electron. So it'll just be a proton, and it won't have a noble gas configuration. But it can gain an electron to become like helium. So we say it's neither a alkali or an neither an alkali metal or a halogen. But it does share some properties of both. Shares some properties with both groups, but I don't expect you guys to know what those properties are. Just know that hydrogen is kind of like in the middle. It's not really, it's technically on the first column, but it's not, it doesn't share the same reactivity as those other metal elements. Okay, so that's all of the chemical families that we'll need to know. Okay, let's move on. Okay, so let's talk about the halogen. What do these elements look like? So here's the picture of the halogen families. So iodine, chlorine is a gas, bromine is a liquid, iodine is a solid. It has this nice purple color. Bromine looks god awful. You never want to work directly with bromine. It's toxic. So yeah, if you have to work with bromine, like if you work in like a synthetic lab, be very careful. Always use the fume hood whenever you're working in the lab. But you see here, it looks like this dark orange amber liquid that you might confuse with like oil, but you don't, because this stuff is toxic. So bromine, just that PSA kind of announcement. If you ever work with bromine, please be careful. But bromine just looks like an awful liquid. Awful to work with too, because it's a liquid, so liquids are kind of hard to measure out. You prefer to work with solids. Gases are another story, but usually we try not to work with gases. Okay, so that's the halogen family. See how what we're doing on time, 6 minutes. I think we'll be able to finish this. We'll be able to wrap up this chapter. Okay, so lastly, we're going to talk about the other families that we didn't get to mention. So let's talk about metals and nonmetals. So metal. Metal is described as a substance that possesses metallic properties of luster, ductility, malleability, and good conductivity of heat and electricity. So the difference between ductility and malleability, ductility, I think you can pull into like wires, and malleability is basically things you can like kind of like bend or bend to the shape. We could double check here. So, actually, let's check here. All right, so yeah, it's kind of like flexibility. It can be bent out of shape while cracking and bending. Some solids can't do that; they'll break. But malleability, a good metal can be bent out of shape without breaking or losing its character. Malleability and electricity here. So things about metals, they lose electrons to form ions, loses electrons to form monatomic, so one atom ions. So we call those ions cations because they're positively charged. So the thing about metallic character, increases from right to left. Whoops. From right to left across any row. Any row of the periodic table. And from top to bottom. From top to bottom in any column. So the trend in metallic character is basically a combination of the ionization energy and the atomic size. Okay, so what does a non-metal do? Well, a non-metal is basically the opposite, and what it does is a substance that possesses non-metallic properties such as being dull, so there's two definitions. So what we mean by dull is like it's the opposite of luster. They don't shine. So basically a property that's opposite of a metal. Such as being dull, they're not malleable, so they're brittle, and they're poor conductors. And a poor conductor of heat and electricity. Non-metals, they don't form ions. They tend to form covalent compounds. So we'll talk more about that later, but it forms covalent bonds to form monatomic anions. So, like, we'll talk more about what that means in the next chapter, because we'll be talking about covalent bonds and ionic bonds. Lastly, we have metalloids. And there are elements or an element that has both. Has both metallic and non-metallic properties. All right, just a few more things to go over and we'll be done here. Non-metallic properties. So lastly, let's look over the classifications in a more let me see here. In a more like generic sense. So here's some physical and chemical properties of metals and nonmetals. So metals, they will tend to lose electrons to form cations. Non-metals, they tend to gain electrons to form anions. So yeah, that's why I told you to kind of ignore what I meant by forming covalent bonds. Because we'll talk about that in the next chapter. So what we mean by covalent bonds is that nonmetals will form a bond with nonmetals, and they'll form a compound. But we'll talk more about that in chapter, I think, 12. So they tend to gain electrons to form anions. That's why in like something like sodium chloride or salt, you have sodium, it will lose the electron to form sodium plus, and chloride will gain an electron to form chloride ion. So metals tend to have 1 or 3 valence electrons. Non-metals tend to have 4 more. And they're also classified by low ionization energies for metals, high ionization energies for nonmetals, because nonmetals are on the right of the periodic table, whereas metals are on to the left. So generally speaking, metals form compounds with nonmetals, but not with other metals. So you never see like a metal like sodium potassium couple. Generally speaking, though, if you go into more specific cases, there are instances in like literary research where that is true, but for our purposes, we're not worrying about that. Non-metals, they can react with other metals and other non-metals. For example, phosphorus trichloride is between 2 non-metals, and like sodium bromide is between a metal and non-metal. And like we talked about, high conductivity and poor conductivity of nonmetals. But a form of carbon is actually a good conductor because graphite has layers that allows conductivity to occur, but don't worry about that. That's just an example. So poor thermal conductivity, but good insulator. So they're opposite of conductors for nonmetals. They're brittle, they're non-ductile, so you can't bend them into shape or draw them onto wires. Whereas metals, they can be deformed and be hammered into different shapes, sheets, and ductile can be drawn to wires. So that's our classification for metals and nonmetals. I tend to ask maybe a few questions about them, but if you could refer back to this chart and kind of rationalize their properties, I think you should be fine. Doing the homework also review will get you to think about this stuff. And lastly, the last slide is our classification here, metals and nonmetals. worry too much about. So just know the general location of the metals, the metalloids and the non-metals, but you should be able to do that on your periodic table because we went over it a couple of times. So just refer back to where the non-metals are. Remember, hydrogen is a non-metal. It's not a metal. And then the metalloids are in the staircase here, but don't worry too much about the metalloids or about their properties. Okay, and then last but not least is, so our general trend in a metallic character is that if we go back looking at our metal, it increases from right to left. So as we go away from the non-metals here into our alkali and alkaline earth, our metallic character increases. And as we go down the table, we get more metallic character. And as you saw on that other slide, as we move from like lithium to potassium, the reactivity actually increased. So that gives us an indication that our metallic character increases as we go down the periodic table. Okay, so that is chapter 11. Sorry we're going a little bit over time, but next time we'll pick up with chapter 12. And depending on how that goes, that might be the last chapter we cover before the midterm, but we'll see. But anyway, reminder that this homework will be due on Thursday, so don't forget to do that. Make sure you don't put it off to the last minute. I always recommend to do a few here and there when you have time, and keep yourself to a tight schedule so you don't forget. But anyway, guys, I'll see you on Thursday, and have a great rest of the week.